So, welcome back after the short break. So, we are talking about the common mode stimulus, and let us see what happens to the circuit when we stimulate the circuit with identical signal at the two inputs. And so, here we do have the small signal equivalent circuit, and here we like to feed the signal, small signal. So, V in 1 equals to V in C. So, same thing, same signal we are feeding here at the other input. So, V in 2 equals to V in C. Now, for our understanding of the circuit, again we are keeping the circuit disconnected here, and we like to see what kind of signal we do get with this stimulus. So, if we are keeping this is disconnected, and if you refer to the circuit here at the transistor level, this is common source amplifier with degenerator, source degenerator. So, this is the source degenerator, and we know its consequence, namely the signal coming at its output, it will be VO2 equals to the input V in C with a minus sign here, and then GM1 RD1 divided by 1 plus GM1 into 2 RT, or you can approximate this by minus V in C GM1 RD. In fact, this one part you can remove. So, we can simply consider GM1 and R2 RT. So, this GM and this GM is getting cancelled. So, same thing for the other output, namely VO1 equals to again minus sign the corresponding input multiplied by RD. So, this is RD1, this is RD2, and then 2 RT. So, note that the signal here and the signal here, they are identical. Now, if I consider on the other hand the signal at the emitter, if I consider the signal at the emitter, it is working as similar to our previous discussion. Before we connect the resistor, these two resistors, we do have signal coming here very close to the applied input voltage, which is V in C, and then Thevenin equivalent resistance, it is approximately 1 by GM1. So, likewise, if I consider the other side, this side, and what we get, it is similar kind of equivalent circuit, namely the signal source, which is close to V in C, and then Thevenin equivalent resistance of 1 by GM2. And note that unlike for differential case, since these two signals, the applied signal at the two inputs, they are in phase, then this signal and this signal, they are in phase. Now, even if we make this connection, since these two signals they are identical, there will not be any change. So, the signal coming at this point, it will be V in C. So, before we make this connection, whatever the signal we are having here and here, they are remaining same even if you make this connection, and that is mainly because the input signal, it is the applied input signal, they are identical and they are in phase. So, I should say that the common mode output, if I say, if I take average of VO 2 and this VO 1, so that gives us the common mode output VOC. So, that is VO 1 plus VO 2 by 2. So, that is remaining same as individual one, namely V in C multiplied by R D divided by 2 R T. In fact, that gives us the common mode gain AC defined as, of course, with a minus sign. We do have a minus sign here. So, AC is which is defined as VOC divided by V in C equals to minus R D by 2 R T. Okay. So, that is the common mode gain. In fact, similar thing you can get for the other differential amplifier realized by BJT. So, in the next slide we do have the corresponding circuit, and here again, even though we do have a small change, small difference in the circuit, namely we do have R pi and R pi here, but all practical purposes, when we stimulate the circuit with identical signal here V in C at input 1 and input 2, then the signal coming here and here, they are identical, and the signal at VO 2 equals to minus minus GM 1 into R C 1 divided by 1 plus GM 1 2 R T into V in C, and same thing we will be getting here also, namely VO 1 is equal to minus GM 2 R C 2 divided by 1 plus GM 2 R 2 R T into V in C. Now, since the signal here and here, they are in phase, even if we make this connection, the signal coming here, it will be remaining unchanged, namely this will be approximately equal to V in C, and as a result these two output, even after making this connection, they are remaining unchanged, and hence VO C, it is equal to approximately GM into RC divided by 1 plus GM into 2 RT into V in C with a minus sign. So, you may ignore this one and then you can remove this GM part. So, that will be equal to minus RC divided by 2 RT into V in C. In fact, that gives us the same expression of common mode gain equals to minus RC divided by 2 RT, right. So, in summary, we got the expression of the common mode gain and differential mode gain whenever we will be going into numerical circuit, then we will see their corresponding values. Now, so far we are talking about the small signal situation. Now, you may recall that while we are applying the signal at the input, definitely we are also applying a meaningful DC. So, now next question is that what may be the meaningful DC, quote and unquote meaningful DC, that can be analyzed by considering large signal behavior of this entire circuit. In fact, not only this voltage, but also we like to know what may be the DC voltage coming at the two outputs, and we like to see whether the two transistors really in good condition or not. So, to understand that, we need to have large signal analysis. Okay. So, before we go into the large signal analysis, of course, I need to say one more thing, that so far we are talking about small signal one at a time, namely differential part and then the common mode part. But then in case you have say both the signals coming together, namely if V in C and the differential part, namely plus V in D by 2 and minus V in D by 2, if they are coming together, then what happens? So, naturally before we make this connection, the situation it was something, but again instead of repeating that, I may directly get into this connection, and then we like to see what may be the condition here and here. So, before you go for large signal analysis, let me do one more small signal analysis, where we are considering both the common mode and differential mode signal together, and we like to see the corresponding output. So, in the next slide we do have the generalized mode of stimulus. So, as I said that at the input we like to give both differential and common mode part together, and probably we can make this connection. Now, let us see if we apply a differential part here, V in D by 2. So, here we do have V in D by 2, and then we do have on the common mode part. Let me use blue color. So, V in C, which is going to both the inputs. So, it is going here as well as here. Now, let us see once we make this connection, then what may be the signal here, what may be the signal here, and what may be the signal here. Now, due to this perfect differential, sorry, this is perfect differential, that means we do have a minus sign here. So, these two differential signal is not having any influence. In fact, for differential component this is supposed to be ground, but then we do have the common mode component. So, the signal coming here, it is only V in C. I should say very close to V in C. It is slightly less, but it is very close to that. And then what happens to this output? We do have the this signal, it is coming in amplified form. So, this differential part, it is it is showing its effect, it is in opposite phase. So, likewise here we do have the effect of differential part, which is in phase of the differential input. Okay. And then we do have the effect of the common mode part, which is of course having smaller amplitude. And so, here we do have the common mode input, which is again getting flipped. Note that for our simplicity, we have considered both the signals are having the same frequency. So, and then if that is the case, then at the two output what we will get, the combined effect of these two, it may be something like this. So, this is the net output we do get at this point, and if I consider the other input, it will be having the corresponding signal like this. So, you can see that this amplitude it is slightly higher because of the common mode component is coming there, and this signal it is slightly less than the red color. So, we can say that at the output we do have both differential as well as common mode part, they are present. So, VOD, if I take the difference of these two signal, will be getting GM1 or GM I should say, GM into RC into V in D. And if I take average of these two signals, average of say this signal and this signal, then what we will be getting is only this part, because they are getting added up and the red portion it is getting cancelled out. So, we can say that VOC, if I take average of the two signal, then VOC equals to GM into RC into V in C. So, that is how the circuit it operates. Now, as a special case, if you consider that let you consider a special case where you would like to give a 0 signal here. That means, if I apply say V in C equals to V in D by 2. So, what happens? So, in this case this part, if it is V in D by 2 and then we do have minus V in D by 2. So, together that gives us a 0 signal here. On the other hand, if I am having this signal equals to V in D by 2. So, this V in D by 2 and this V in D by 2 together it gives us V in D. So, the signal at this point with respect to ground, it is V in D by 2. So, such kind of stimulus, namely if we have a signal only at one side and then other side it is say ground, it is referred as pseudo differential stimulus. Many a times, suppose you do have an amplifier like this, we like to give signal only at one end and then of course, along with the DC, while at the other input we like to give only this DC, and the signal here, it is whatever the complete signal, you may say that this is V in, incidentally that is this V in D. For such case, obviously you will be getting a signal here which is V in C, and this signal it is if you see here, it is V in D by 2, and the corresponding signal here, because the common mode gain and differential mode gain, they are quite different. Sorry, I have committed a mistake here. VOC, it will be V in C multiplied by GM into RC divided by 1 plus 2 GM into RT. Sorry. Yeah. So, since this gain is low, that is why we are getting smaller signal. So, now in this pseudo differential case, whenever we are considering this common mode signal, it is half of the differential signal. Then since this signal it is small, even in this case the net voltage, which is this VO2, and the net voltage here so this net voltage here, which is VO1, since this part it is very small, so we can approximate that this output and this output, they are almost like a differential. So, based on the logic, if the common mode gain, this AC, it is very small compared to this AD, then you can say that even if we stimulate the circuit in this pseudo differential form, the corresponding output, they are very close to like a differential operation, and that is why it is referred as pseudo differential mode of operation, right. And now we are in a position to go for the large signal analysis. So, in the next slide we are going to talk about large signal analysis, and we like to see the DC operating point of the amplifier. So, again going back to the circuit here, the basic model here, where we do have the differential amplifier, which is getting stimulated by a pair of signal accompanying same amount of DC voltage. And here we do have the corresponding implementation. Now, we are going to talk about what is the role of this DC voltage and what may be the range of this DC voltage, and if we vary this DC voltage, what may be the situation at the output. Now, since this DC voltage, it is applied to both the input terminal, to understand this circuit operation, we do not require to split this circuit. In fact, we can keep the circuit like this, and at the two inputs. So, at both the inputs, we shall apply a DC voltage called V in C, and then we can observe the corresponding DC voltage here and DC voltage here. So, we can vary this voltage, and then we can see what it may happen to DC voltage here as well as here. Now, we have so we do not require this kind of split. So, we are considering this is connected, and hence our subsequent discussion, it will be with this circuit. We may not be going back to the split one. Now, coming back to what we said is that if I vary this voltage, and then if we observe the voltage at the two outputs, definitely they are also defining the condition of transistor 1 and transistor 2. And for good operation of the circuit, we want both the transistors should be in active region of operation. So, the range of this voltage, it should be such that both the transistors should be in active region of operation. Now, we also have said that to make ACD and ADC to 0, we say that Q1 and Q2 are identical and RC1 equals to RC2, right. And since they are identical, probably we can consider the entire circuit together, and in fact, since these two are identical and these two are identical, we can say that voltage here and voltage here, they will be same. So, we can simply consider it is a folded circuit, where Q1 and Q2 we can overlap together, and then we do have RT here. So, likewise we do have RC1 and RC2, they are coming in parallel, and here you do have Q1 and Q2, they are coming in parallel, and the voltage you are applying here, it is this V in C, input common mode voltage. Now, if you analyze this circuit, of course, depending on this voltage, we will be getting a voltage here, and then that will define this current, and that current it is flowing here. So, we do have a DC supply voltage VCC. So, we can make a drop of this voltage, and that gives us the corresponding collector voltage. In fact, if you go step by step to that, for a given V in C, so what is the emitter voltage? So, emitter voltage at this node or in this you say merged circuit, the emitter voltage equals to V in C minus VBE on. So, it may be around 0.6 or 0.3 depending on the transistor's material. So, that gives us the voltage here, and hence the current flowing through this RT equals to V in C minus VBE on divided by RT. In fact, this current, it is flowing through both Q1 and Q2. So, here also you can say this is I R T, which is summation of the two emitter currents, and if I say that both of the transistors are identical. So, we can say that half of this current is emitter current, and practically they are defining the corresponding collector current. So, the voltage at the two output nodes, if I say that VO DC equals to VCC minus RC, RC1 or RC2, both are same, this multiplied by IRT by 2. So, that gives us the corresponding collector voltage, and we do have the emitter voltage. So, now we have to apply a meaningful voltage here, so that both the transistors should be in active region of operation. Not only they should be in active region of operation, it should be having sufficient, the voltage here should be having sufficient room for the signal, so that we can have good amount of signal amplitude, it should be able to accommodate. So, the range over which this voltage it is allowed, it is referred as common mode range, and in this case of course, it depends on the corresponding value of RT and RC. So, whenever we will be talking about numerical examples, where we will be having value of this RT and RC and the supply voltage, there we shall see the upper limit and lower limit of this input common mode voltage. only thing is that qualitatively. So, these are the expressions, but qualitatively I must say that it is having a good range. So, it is not necessary that we need to have very precise DC voltage here for proper operation. It will be having a good range over which the circuit it will be working fine. Only thing is that depending on this value of this V in C, the corresponding collector current it may vary. So, I should say that collector current is strong function of V in C, and hence all the small signal parameters, namely Gm and R naught and so they are strong function of this voltage. But as long as the devices are in active region of operation, typically they do not have any problem for proper functionality of the differential amplifier. Now, once you get the DC operating point, next thing is that what may be the possible signal swing. So, let us see in the next slide. Yeah. So, input, in fact, we already have discussed this point, the input common mode range. So, the range over which this common DC voltage it is allowed to vary. Now, next thing is that once we have this V in C, and then what may be the range of this voltage over which the transistor, both the transistors they are remaining in active region of operation. So, if you see the range, pictorially, suppose we do have the total voltage range. So, this is VCC and this is ground, and suppose this input common mode voltage it should be higher than 0.6 or VB1. So, that at least we will be getting a meaningful voltage here. So, V in C it should be higher than say 0.6 and above. So, that is the lower limit of this, and then for a given V in C we do have some current flow here, and then of course, there will be some IR drop. So, the corresponding DC voltage here it may be somewhere here. Now, this is VO DC. Now, this DC voltage it can go as high as, or it may go close to the VCC. On the other hand, it can go as low as, suppose we do have some V in C given to us. So, V in C we are expecting this should be higher than this lower limit. So, suppose this V in C it is given to us, then the VO individual output VO1 and VO2 with respect to this DC it can go as high as towards the VCC, or it can go as low as towards the V in C, maybe with a margin of 0.2 or 0.3. So, whatever the range we are talking here, this side and this side, so that is referred as the possible signal swing. Now, for a given input DC voltage, we want this DC voltage should be towards the middle of it. So, that the positive swing of the output signal and negative swing of the output signal they should be equal. So, that gives us the maximum possible not only maximum possible peak to peak voltage, but also that will be helping us to get the maximum amplitude of the sinusoidal signal, right. So, again as I said that whenever we will be going through some numerical examples, we shall explain little detail of how to pick the right value of the resistances and this resistor. So, similar to BJT, for MOSFET circuit also we do have similar kind of situation, namely the DC operating point, it is a strong function of the input common mode voltage. So, suppose we do have input common mode voltage coming to the gate of transistor 1 and transistor 2, and that essentially, so this is V in C. So, that defines the gate voltage here. Now, again here also we are assuming these two transistors, they are identical, and these two resistors, they are identical, and since both the gate nodes, they are getting the same voltage, probably we can fold it and we can equivalently say that we do have a single chain where we do have M1 and M2, they are connected in parallel way, and then here we do have V in C, and then we do have RT here, and then we do have two RDs are in parallel. In fact, if they are equal, you may say that simply RD by 2, and then here we do have the VDD. Now, for this circuit, if you may recall, if we analyze this loop, and then if the parameter of the transistors are given, namely threshold voltage and transconductance factor, so from that we can find what will be the corresponding current flow here for a given value of this voltage. So, if you analyze this circuit, what we can say that suppose this circuit, the combined resistors, they do have transconductance factor of say K W by L, it is given to us, then it is having VGS, and then also if its threshold voltage is given to us, then we can say that V in C equals to VGS of transistor 1 or 2 plus the total current. So, if I say this is the current is say I R T. So, I R T multiplied by R T. So, this is one equation. Another equation we can get is that I R T should be equal to this K W by L. This is combined transistors M1 plus M2 together multiplied by half, and then the corresponding VGS of transistor 1 2 minus VTH square. So, we are dropping 1 plus lambda VDS part. So, if you solve say if you consider this equation and this equation, and then if you solve, then you can find the value of this current flow through this RT, and then you can say half of this IRT, it is flowing through this resistor and this resistor. From that you can find what will be the corresponding drop, and that gives us the DC voltage, common DC voltage VO DC equals to VDD minus RD multiplied by IRT by 2, right. So, that is how we can get the output DC voltage. In fact, either you consider this circuit where the drop here it is RD by 2 multiplied by IRT, or if you consider half of this circuit where current is half and the resistance is RD, whatever it is. So, we got the expression of output voltage, DC output voltage for a given input voltage. Now, again this voltage it may be having a range, and this voltage definitely it should be higher than threshold voltage of the transistor, so that we can get a positive voltage, and hence it will be having some current flow here, and that current flow, it will be flowing through this resistor, keeping these two devices in active condition, and preferably the drain voltage and gate voltage should be such that both the transistors should be in saturation region. And not only they should be in saturation region, if we have a DC voltage here and DC voltage here, it should be such that signal should be having some headroom. So, again this is also important aspect, but unless we do have numerical values of the supply voltage and resistors, probably it will be a little too hypothetical to analyze. So, once we will be going through numerical examples, then we will be talking about the calculation of input common mode range and DC operating point, and then the corresponding output signal swing. Now, at the input now, if we apply a voltage, so far we are talking about small signal. Now, in case if we apply say large signal, keeping this voltage constant, then what happens? So, if I say that it is perfectly differential, namely this is V in D by 2 and this is minus V in D by 2. So, if I make these two signals 0, obviously voltage here and voltage here, they are same, namely V O D C, and this is of course V in C. Assuming that V in C it is having a value which is within its acceptable range, and then output voltage it is also having meaningful value. Now, if I increase this voltage, subsequently if I am also increasing this voltage with this minus sign. So, what we are expecting here, it is this voltage it will increase with respect to its DC, and this voltage will decrease with respect to the DC. So, if we plot the difference of these two voltages called VOD with increase of this V in D, then what we can get here, it is input to output transfer characteristic, but then input it is in differential form, and so is the corresponding output. So, if the input is very small, the behavior here to here it was quite linear. So, this may be linear, but as you are increasing this input voltage beyond some limit, then what will happen is this may enter into nonlinear characteristic. Likewise, this side also it will be entering into nonlinear characteristic, and this VOD it is defined as capital V O1 minus capital V O2. Note that this VO1 and VO2 they are representing large signal voltage. Both of them are having the same DC voltage of VODC, but then once we subtract it, that got removed. So, range of this VOD it is in fact positive and negative. This is 0 level and this is positive and this is negative. So, same thing for V in. If I am making these two voltages together, but if we are making this voltage it is higher and higher, then we may define this V in D as capital V in 1 minus capital V in 2, and both of them they are having this V in C DC. So, voltage here it is V in 1 capital V in 1 and voltage here it is V in 2, and both of them are having the common DC and then differential part. Now, whenever we are talking about small signal, what we have essentially considered is that range of this input voltage it is small enough, so that we are talking in the small range, and slope of this characteristic curve it is the gain, small signal gain. As we increase this voltage beyond certain range, then it may enters into the saturated condition. So, whenever we are talking about differential amplifier and if we are restricting the operation within this linear range, then it can be treated as a good amplifier having good linearity between input to output. But once we go for and some other application where circuit is entering into the saturated situation, then also it is having some application, but the circuit will not be called it is a linear circuit. In fact, then circuit it becomes like a comparator. So, the basic differential amplifier structure can be used for both for amplification purpose for analog application, as well as it can be used for comparator. So, later whenever the situation permits, we may elaborate on that, but just I like to say that differential amplifier, whatever the amplifier we have discussed, it is having a specific application not only for analog, but it is also having some application called mixed signal, where the output it may be more like a logic signal, high or low. I think yeah, that's all we do have. So, to conclude, to summarize what we have discussed today, we started with small signal equivalent circuit for differential amplifier realized in either in BJT or MOSFET version, and then we have talked about small signal analysis for differential amplifier, specifically for 3 different modes of operation, extensively for differential mode and common mode, and then also we have talked about generalized stimulus, and pseudo differential is a special operation. Then we have talked about the large signal analysis, where we mentioned about the importance of DC operating point, and the DC operating point it is a strong function of the input common mode voltage V in C, which also defines the output difference DC voltage, and both this input common mode voltage and output DC voltage and the range of operation of the transistor, they are defining the output swing. So, we did not get a chance to elaborate on these 2 topics, particularly input common mode range and output swing, because it may be difficult to appreciate without any numerical value. So, whenever we will be talking about numerical examples, we shall further elaborate on these parameters, and so our next discussion it will be numerical examples on differential amplifier, which will be covered in the next lecture. I think that is all. Thank you for listening.